In this video, we're going to finish section 4.1 by talking a little bit about differentiation and uniform convergence. And unfortunately, this isn't as nice as integration. So here are two examples of functions, sequences of functions that converge uniformly, but where their derivatives do all kinds of nasty things. So first example, we're going to let fn of x be 1 over n times the sine of n of, we can even make it n squared times x. Then fn converges uniformly to 0. Just pick your big N to be 1 over epsilon. But you can compute fn prime of x is actually n times the cosine of n squared x. Those aren't even uniformly bounded. They're getting bigger and bigger and bigger, which is a thing which does not converge. And second example is let's let fn of x, we'll make it the square root of x squared. Nifty trick, the absolute value of x is the square root of x squared. Sometimes this makes it easier to do computations involving absolute values, and I'm going to add a 1 over n squared here. And that makes this function completely differentiable. Fn prime of x is, as it happens, x divided by the square root of x squared plus 1 over n squared. Then we've got that fn is converging uniformly to f, where you can show that this converges uniformly to the absolute value of x. This 1 over n squared smooths things out at the origin a little bit. Fn prime is converging to a function g, converges in fact uniformly to g, where g of x is this is the following piece what is defined thing. It's 1 if x is positive, minus 1 if x is negative, and 0 if x is equal to 0. This is not uniform convergence. The fn primes are continuous, g is not, so if fn converged uniformly to g, we'd have that g was continuous. But notice that f prime of 0 doesn't exist. So in particular, f prime of 0 is not the same thing as g of 0. The derivative of the limit is often not the limit of the derivatives. So if you want to talk about convergence and derivatives of limits, you have to assume that the derivatives converge. You cannot just assume that the functions converge and then try to talk about the derivative of the limit. You have to assume the derivative converge. So let's make this precise. So here is what we can prove. We're going to start with an interval in the real numbers. And let's let f sub n and g be functions that go from defined on our interval I, so functions from I to the real numbers. And then we are going to suppose the following nice properties. First off, we need that each fn is continuously differentiable. So not only does it have a derivative, it has a derivative that is continuous. And we're going to say, secondly, that fn prime is going to converge uniformly to g on our interval I. And the third thing we're going to need is that the fn's converge at least one point. We're going to end up proving that if they converge at one point, they converge at all points. But we're only going to assume that there is one point C in our interval I such that the sequence fn of C, this is the sequence where you pick your points and you take the first function at C, the second function, the third function. This has to converge in the sense of section 1.3, so all the way back last semester. Then the conclusion is that the fn's converge everywhere. There is a f from our interval I defined on our interval is such that fn converges to f pointwise. In a bounded interval, or a closed bounded interval, at least, you can show that fn converges to f uniformly, but for an unbounded interval, pointwise might be the best you can do. And f is differentiable. And f prime is equal to g everywhere in our interval. Let's prove this. So first thing to notice is that by theorem 4.1.6 from the last video, g is continuous. All right. Now, because the fn primes are continuous, by the fundamental theorem of calculus, if x is in our interval, then we can notice that fn of x is equal to fn of c plus the integral from c to x fn prime. Now we assume that this fn of c that converges as n goes to infinity, and from theorem 4.1.9 we also know that this integral converges. So we're going to define little f of x, that's the limit as n goes to infinity, fn of c, which is just a number, that's not a function, and then we add to that the integral from c to x of g. And then by the previous theorem, theorem 4.1.9, we have that fn converges to f pointwise. And then by the fundamental theorem of calculus, we have that f prime equals g. So that's not too terrible. That's not too hard to prove. But no, but it only works if you have these fairly strong assumptions. You need convergence of the derivatives and not necessarily of the underlying function. You can dispense with this assumption of continuous differentiability. You can prove this if Fn is just differentiable, but you don't assume the derivative is continuous. You need a little bit more assumptions on convergence. You need to move this part back up into your assumption, but the proof of that is much nastier. Now we are going to start section 2 on formal power series. Power series are a particular and very important set of sequences of functions that sometimes converge, sometimes diverge. Why don't I write down the definition and then we can talk about convergence a little bit. So here is the definition of a formal power series. So a formal power series is a sum that looks like this. For some fixed C and R and some sequence of numbers starting at 0 and going to infinity. And I want to emphasize that a formal power series is really just a way of writing down a sequence. The formal power series is really the sequence of coefficients plus the base point in C. The x to the n's or the x minus c to the n's, you can think of them as just clothespins on which you're hanging the numbers an. So you can write down a formal power series for any sequence of numbers you want. Sometimes that gives you an interesting function and sometimes it doesn't. We'll talk about that at a little bit later. So now, when talking about formal power series, we're going to say that 0 to the 0, we're going to say that's 1. Normally it's an undefined form, but if it's x minus c to the n, where x happens to be c and n happens to be 0, we're going to say, no, we're going to just say that to be 1. So now suppose that x is a real number. And then, now, this is mostly rehashing the definition of convergent series from way back in section 1.4, but let's write it out. If this limit exists, limit as big N goes to infinity, you sum, you take only finitely many terms, and since the ANs are real numbers, x minus c to the n is a real number, so each of these finite sums is, a pretty reasonable thing. It behaves like you want. If this limit exists, and is a real number, we're often pretty vague on whether we're often unsure whether we want to say converging to infinity counts as converging, or rather, there are lots of circumstances where we want to say converging to infinity counts as converging, and other circumstances where we want to say converging to infinity does not count as converging. In this particular case, yes, converging to infinity does not count as converging, so we'll specify the limit has to be a real number. We say the power series converges at x. And otherwise, if that limit does not exist, if either it's an oscillating thing, if n is 1, x is -1, is c is 0, so you're always bumping back and forth between -1 and 1, or if an is 1, x is 1, c is 0, so your limit is just getting bigger and bigger, we say the power series diverges at x. And let me give you one example to illustrate what I mean by formal power series. The two power series, let's look at these two power series. Let's start at 1. You can start at 0 and replace n by n minus 1 if you want. So n factorial times x to the n. N factorial, you'll note, is getting bigger and bigger. And this other power series, n to the n times x to the n, these guys both diverge for all x except 0. You can check this using, I think the ratio test works better for the first one. You really need the root test for the second one. And they both converge. Since we started at n equal 1, they both converge to 0 if x is 0, because if x is 0, every single term you add is 0, and 0 plus 0 plus 0 plus 0 plus 0, we say that converges to 0. And so for any given x, these two series, they act the same. Either they diverge or they converge to 0. But nevertheless, we think of these as two different power series, and that's why we call it a formal power series and not just, a fancy way of writing a function. There's still some structure in here that still exists, even if these guys don't give us nice functions of x. Let me give you now an example of a better behaved power series. N factorial x to the n to the n, x to the n are technically power series, but most of the time we care about power series that converge at more than one point. So the geometric series is a power series. Or rather, this is a bunch of geometric series, one and for each x. And from section 1.4, and then by proposition 1.4.4, the series converges if the absolute value of x is less than 1 and it diverges if the absolute value of x is greater than or equal to 1. You have to check the two cases where x is plus 1 and x is minus 1 individually. In proposition 1.4 but it's nonetheless true. And it turns out that power series, if you're given a power series, you're always going to have a result something like this. That there's always going to be some number where the series converges as x is close enough to the base point, which in this case is 0. And let's write this as a proposition. Your book does this a little bit differently. Your book does this using explicitly the root test. I don't want to do it that way, so I'm going to phrase this a little bit differently than your book's proposition 4.2.4. So let's let some an x minus c to the n be a power series. And let's suppose the power series converges at the point x equals z for some number z in the real numbers that isn't the base point. And then two things are true. If y is a real number, and the distance from y to c is strictly less than the distance from z to c, then the power series converges. At the point y. And we can say something stronger. We can now say it since in the last video we defined uniform convergence. If R is a positive real number that's less than the distance from z to c, then the series converges uniformly. On this set that I'm going to write 3 different ways. This B bar of CR is how we're going to write this set in chapter 5. It's just the interval from C minus R to C plus R, closed interval including the endpoints. And I'll point out that this is also the set of all real numbers whose distance to C is less than or equal to R. And that's very abstract, so let's have a picture. Here is our number line. Here is our base point C. And then out here, we've got the number Z where it converges. And then here on the other side, there's another number whose distance this number as it happens, it's c minus z minus c. So the distances on the two sides are the same. And then everywhere in here, everywhere between c and z, and also between c and c minus z minus c, we converge. And moreover, so on this region, so this is length r on both sides, we converge uniformly. And you can get your radius of convergence as close to z as you want, but the penalty for that, of course, is that you're going to converge slower and slower, and we don't know what happens at this other point over here. We don't necessarily know what happens outside it when you're farther away from C than Z, but we do know if you're closer to C than Z, then you're definitely going to converge, and you can get uniform convergence by pinching in a little bit. So let's go ahead and prove this. Now we are going to use some results from chapter 1, but hopefully I'll pick ones that are a little bit more intuitive, a little easier to understand than the root test. So we've got that our power series converges at z minus c. So this series this thing converges. And so what does that mean? So by proposition 1.4.2, a necessary but not sufficient condition for a series to converge is that the sequence of terms you're adding up has to go to 0. This is a fact that isn't formally stated in your book, but which we did prove last semester. It's not hard to prove. So that means that the supremum the biggest that these things get, let's take the absolute value. Is some finite number. So all we've used so far is the fact that if you're a convergent series, then your individual terms, they have to be they have to converge to 0, and so in particular, they have to be bounded. And now let's look at what happens elsewhere. Let's let f sub n of x be our partial sum. That's a perfectly good function to find on all the real numbers. And now let's notice that if big M is bigger than big N, then f sub m of x minus f sub n of x, that's the sum from n equals big N plus 1. It's all the terms in Fm that aren't also in Fn. And so we can take the absolute value, fm of x minus fn of x. You use the triangle inequality and induction and a bunch of other things. And then x minus c to the n. And then we've got that an times z minus c to the n is less than our little m. So we can write this as sum from n equals big N plus 1 to big M. And then we've got x minus c over z minus c, whole thing to the n. And then we've got our little m, which we can put out front if we want. It's a constant. We can go ahead and move it out of the sum if we feel like. And then we've got a constant times a geometric series. And we know how to sum geometric series. This comes out to our little m hangs out front. And then we've got our difference our ratio x minus c over z minus c, whole thing to the big N plus 1. Then we subtract off our little m. And then we can go ahead and throw away the second term. It's a negative number, or at least a non-positive number. Okay, so we've got that. We've got this upper bound on our difference between our two functions. So let's notice that if x minus c is less than z minus c, then the limit as big N goes to infinity of our difference is 0. And so that means for every epsilon, if n is big enough, this is less than epsilon. So for every epsilon, if n is big enough, fm minus fn is less than epsilon. So it's not too hard to show that this means that the sequence fn of x is Cauchy, and we know that Cauchy sequences of real numbers are convergent. Why don't I write that out in a little bit more detail when we do the uniform convergence uniformly Cauchy argument. So let's do the second part. Let's let R be between z minus c. And we'll go ahead and pick an epsilon bigger than 0 and let k be a natural number that is such that little m times r over z minus c. R over z minus c is less than 1. So if you take this to the k plus 1th power, it is less than epsilon. This goes to 0 as k goes to infinity. So we just pick k big enough that this is less than epsilon. And then if x is in our interval, I'm going to call this B bar of CR just because we're going to see that an awful lot in chapter 5 and I want you to start getting used to it. And N, M are both bigger than or equal to K, then either N equals M and trivial case Fn of x minus Fm of x is 0, which is certainly less than epsilon, or M is bigger than N is bigger than or equal to K, and then our difference Fm of x minus Fn of x less than or equal to M times x minus c over z minus c to the n plus 1. That is all less than or equal to, M stays the same, x minus c is less than or equal to r over z minus c, and then n is bigger than k, r over z minus c is less than 1, so this is less than just taking it to the k plus 1th power, which is less than epsilon. Thus, this sequence is uniformly Cauchy. On our little interval on B bar of CR. So by exercise 4.1.5, Fn converges uniformly on this interval. Let's wrap up this video by stating a consequence of the previous proposition. This is sort of another way to state it. This is how your book puts it. So we start with a power series. Then there is a unique that is, there is exactly one number R. It's allowed to be 0 and it's allowed to be infinity. So it's what we call an extended real number such that we've got the following things. First, if the distance from x to c is less than r, the series converges. And on the other hand, if x minus c is bigger than r, the series diverges. There are some series that converge at c plus r and c minus r. There are some series that diverge at c plus r and c minus r. There are some that converge at c plus r and diverge at c minus r. So we've always got these two weird points where your distance to c is exactly equal to r, but for all the rest of the points, we have this very neat relationship. And the last part is that if little r is between 0 and big R, this doesn't happen if big R is equal to 0, but it does work for any positive R. The series converges uniformly on this interval C minus R up to C plus R. And the proof is not hard. Essentially, we've done all of the work in the previous proposition. You just let R be the supremum of the set of all Z minus C such that the power series, or rather in the series, the sum converges. All right, the series converges if Z equals C, because then you've just got the A naught term and then all the other terms are 0. So R is at least C minus C is 0. So R is a non-negative, so our radius is non-negative. And in particular, we're taking the supremum of a non-empty set. And then if X minus C is greater than R, then X minus C, it's not in the set. It's bigger than the supremum, so it can't be in the set of all Z minus C such that the series converges at Z. So the series diverges because it doesn't converge. And then if X minus C is less than R, X minus C is not the upper bound on that set. It's less than the least upper bound. Then X minus C, it has to be less than Z minus C for some Z, such that the series converges. And by the proposition and by a very similar argument that I think I will not read out, you can prove part C also follows directly from the proposition.